Welcome to Siemens Online Registered Installer Training, Module 4, Optical Fiber Cabling. To start, let's review the construction for an optical fiber cable. It all starts with the optical fiber, which is the core or glass itself. And the purpose of that is actually where the optical transmission happens. And the size of the core ranges from 8.3 to 10 microns for single mode versus 50 microns or 62.5 microns, 62.5 microns for multi-mode. Now the cladding surrounds the core, and the cladding is really it's got a lower index of refraction, which is really just designed to reflect the light back into the core as it travels down there. It's 125 microns regardless of size, whether it's single mode and multi-mode, and the two of those are inherently designed to be together and can't be separated. They're manufactured together, and that won't change. During fiber preparation, you will, however, in some cases, remove the coating, which is kind of more of an acrylic material to provide physical protection for the fiber. And in nearly all cases, that's 250 microns in size. So if you want to factor that in and get an overall indication of size, the typical thickness of a human hair is approximately 80 microns. So we're talking a very small size when it actually gets down to the fiber. Now, beyond the coating, you will, in many cases, coating in 250 micron is referred to kind of more of a loose tube construction. In some cases, fiber is actually constructed with just that 250 micron coating. In other cases, you'll have a tight buffered fiber, in which case there's a colored buffer that goes around the coating that builds it up to approximately 900 microns in size for termination. And then surrounding that, you may have a number of elements. Primarily, you're going to have a strength member in there, which is typically like a Kevlar, which provides kind of longitudinal strength on the fiber. There may be a plastic strength member inside of there, a ripcord inside of there, and then surrounded by the overall jacket. And strand counts obviously can vary from as small as 1 or 2 fibers up to, depending on the constructions of fibers, well over 1,000 fibers in a single jacket. Now, there are perhaps different performance levels within the multi-mode and single-mode fiber families, but they're effectively the two primary types of fiber that you're going to see. So the optical light itself travels in waves that are referred to as modes. And in the case of multi-mode, it's exactly that. It's a mode, being a path of light that follows traveling down the fiber. A multi-mode fiber has more than one mode of light. The typical size that we referred to already are obviously 50 micron as well as 62 micron. When the other option is single mode fiber. Single mode fiber is intended for longer distances, and it actually operates using a single mode of light, which actually makes it less expensive to produce. However, due to the smaller core size, it's a little bit more challenging on the termination side. So this slide is just here, it's kind of a reference point to give a little bit of background on some of the light sources that are used for transmitting signals on optical fiber cabling. And the first on top is an LED light source, or a light emitting diode. And those have been around for a long time, primarily intended for low speed applications. They're very cost effective to use, but they are limited to typically around 100 megabits per second or less. So when the need for gigabit speeds and 10 gigabit speeds came out, there was a need for a different light source. And the next one in line was a VCSEL source, which is a vertical cavity surface emitting laser, kind of an inexpensive laser that would still not be the price of a full laser source, but still allow transmission speeds at the time of up to 10 gigabits per second. And now that's actually extended up beyond that to, up to the nearly 100 gigabit per second range. By comparison, laser sources have been used primarily, almost exclusively, for single mode fiber for a number of years. And the cost of a laser is obviously higher than both an LED and a VCSEL, but the speeds it operates at, it's in excess of 100 gigabits per second, probably up in the terabit speeds, but it's certainly still capable of operating at lower speeds, a little bit more cost effectively. But just to give you some background on some of the terminology used and the language used, not only for the transmission of the optical fiber, but some of the language that's used in the test equipment as well. Now this table really just provides kind of a high-level comparison of some of the considerations that come into play when multi-mode fiber is used versus when single-mode fiber is used. And as a general rule, if you walk down the chart, the electronics for single-mode are typically higher simply because of the laser source. The connectivity costs of the single mode are typically also a little bit higher because the tolerance is associated with the smaller cores. We mentioned it's 8.3 to 10 microns versus a 50 or 60 micron core, so it's important to have that level of precision available. In terms of the cable cost itself, it's much lower to develop single mode fiber simply because you're only worried about a single mode, not multiple modes. And when it comes to installation, you're again looking at lower costs for multi-mode simply because it's a little bit easier to do terminations and not worry about the higher precision level that comes with single mode fiber. When it comes to the attenuation or the loss of the cable, it's much higher for multi-mode, so they're limited in distances compared to the applications associated with single mode, which are typically running into the tens and plus of kilometer distance capability. And also as it relates to bandwidth, multi-mode has a lower bandwidth simply with that taking those multiple modes of light and combining them back again versus a single mode of light available with single mode fiber. So when you look at the distances here, you can kind of get an idea of how that correlates in terms of overall application speeds and the associated distances. And you can see single mode is much farther. There's a price to be paid for that. So where you'll typically see multi-mode fiber is in local area networks and I would say, small to medium sized data centers. And then for single mode, you're going to see those in wide area networks, campus area networks, and even metropolitan area networks between cities. But you'll also see those potentially in some of the hyperscale style data centers where the need for higher speeds at somewhat extended distances are required. Now this table identifies the different performances between the different cable types that we've kind of identified, although not as fully as we have here. There's a couple listed in gray, kind of washed out a little bit, which are the 62.5 micron multi-mode referred to as OM1 and the 50 micron multi-mode referred to as OM2. They're really just grayed out because they're not really recommended for any new installations anymore. They're kind of an annex within the TIA standards, but they're just the data here has been provided for reference. And these were really kind of, we'll still find a fair amount of this, but it's going to be more for customers that have existing cabling plants, and in some cases they either want to continue that or just have an extension of that somewhere on their facility. But for new constructions, we really want to focus on the OM3 and OM4 laser optimized multi-mode fiber. And again, that laser optimized reference comes into play where the VCSELs came in, because the VCSELs are a form of laser, so the fiber is effectively ensured that with a smaller core that the VCSEL transmits at, it's got a cleaner core, where historically the OM1 and OM2, the core wasn't always the best part to transmit down. So laser optimized has that reference point for that. And what you'll see for these is they not only have the overfilled modal bandwidth that's capable of even the OM1 or OM2 fiber, but it has effective modal bandwidth, which really gives you a better indication of how it's going to handle the performance for VCSEL style applications. When you get into single mode fiber, you'll see that there's really just boils down to your attenuation level, and it's based on cable construction. So your inside plant cable has an attenuation of 1.0 dBs per kilometer at both 1310 and 1550 nanometers. The indoor-outdoor cable is a half a dB, and the OSP cable is 0.4 dB. And that kind of relates to the fact that you can expect some of the indoor-outdoor and certainly the OSP cable to be going slightly farther, so having that lower attenuation could be helpful. On the next few slides, we're going to talk a little bit about the cable constructions themselves and the environments in which they're used. So at a very basic level, there's usually two types of fiber constructions as it relates to the construction of the fiber cable itself that we referred to on a couple slides back. And the first is the tight buffered, which is 900 micron buffered fibers. That's pretty common for inside plant cables, and it's great because it just allows itself to go right to opening up the jacket to doing the termination. Now on the right, we've got the loose tube 250 micron coated fibers, okay? And what those are really intended for is designed because you can effectively make a smaller overall cable diameter with 250 micron versus 900. You might have to do some cable preparation when it actually comes time for termination. And in some cases, if you have perhaps water blocking gels in there, it's more friendly than it is for the 900 micron buffered fibers as well. So you'll typically see the coated fibers in indoor, outdoor, outside plant applications, and the tight buffered fibers in indoor applications. There's also a kind of a third type that's referred to as ribbon fiber, where you have individual strands of 12 on a single laminate. We're not really going to cover that here in this presentation because that's really more of a hyperscale customer with, really talking about excessively high strand count. So it's very unlikely you'll run into those on a daily basis of any kind. But should you come across those opportunities, Siemens does have solutions to discuss ribbon fiber. Okay, so like we mentioned, regardless of whether it's copper or fiber cable, you have this kind of inside plant or indoor cable, as well as an indoor-outdoor and an outside plant. So we'll start with the indoor cable, and you'll hear this referred to as perhaps indoor cable. You might hear it as ISP for inside plant cable, or indoor tight buffered cable, or inside plant cable. There's a number of different language and terms that you'll hear people refer to that. But they're talking about applications where the cable is going to be running within a building. And that's construction is almost exclusively going to be tight buffered fiber, and in some cases may have an interlocking armored construction, simply because having an interlocking armored construction provides a physical protection of the fiber. Without that, you typically want fiber to be running inside of a conduit or a flexible conduit of some kind to provide the physical protection, because they're usually transmitting significant amounts of data and you don't want any physical damage to come to them. For the jacket ratings, it's going to be a plenum or riser opportunity, and we referenced in earlier modules about the language. These are the NEC terms. So OFNP, optical fiber non-conductive plenum. OFCP is optical fiber conductive plenum, and then the same notations for riser cable. In terms of the jacket colors for indoor cable, you're going to see orange jackets for OM1 and OM2 fiber. You'll see aqua for OM3 or OM4 laser optimized fiber, and yellow for all single mode fiber. For indoor-outdoor cable, which is cable you're going to have installed external to the building, come into the building, and continue on within the building, so you're kind of paying so you don't have to make that transition. Those constructions can range from tight buffered or loose tube, depending on the choice and the application. In a lot of cases, you'll see indoor-outdoor cable used for scenarios where, say for example, you maybe have a parking garage or an extended distance that leaves the building for maybe a security shack, something along those lines where you need to go extended distances and then transition back into the building, so well beyond the 100 meters of copper cabling. The jacket ratings kind of stay the same because they still have to have a rating when they're inside the building, so you either have a plenum or riser construction. In this case, because of the range of these and the additional work that's required in this jacketing material, you're primarily going to find just a single jacket color for this, which is typically going to be black for these cables. And since they have to have some level of moisture resistance, you'll find various methods implemented, whether it could be a gel construction, it could be a powder-based prevention, or absorbent yarns or tapes. And finally, the third of the cable types, which is the outside plant or OSP cable. In this case, exclusively, you're talking about cables that are really probably going to go between two locations, two buildings, where the cable is exclusively traveling outdoors. Now, as a reminder, when you come into the building with a outside plant cable, since it doesn't have an indoor rating like a plenum or riser jacket, you either have to install it within a conduit or transition to an inside plant or indoor-outdoor cable within the first 50 feet of the building for safety ratings. So the jacket ratings you see here are not, aren't going to be plenum or riser. It's going to be a MDPE, which is a medium density polyethylene jacket. And these cables are, I would say, exclusively loose tube construction, 250 micron cable, because simply a couple of reasons, whether it's armored or not. A couple of reasons is that it's a little bit more friendly to the gel material that's used for the water blocking, and that gel material is very good at water blocking, very not pleasant to clean off the fiber. You usually use some special cleaning agents like Icky Pick to get that gel off the fiber prior to terminations or transitions. But you're really focused on having smaller diameters here, and in many cases these fiber cables can have higher strand counts, so the loose tube constructions here make sense. Now, as you see on this slide, there are some color codes that TIA actually specifies, and they're exactly what we've talked about, primarily for the inside plant type of cables, where it's orange for the kind of legacy 50 and 62.5 micron OM1 and OM2 fiber, aqua for the OM3 and OM4 laser optimized multimode, and yellow for the single mode. In some, there are some variations. You might see gray jackets used for the 62.5 in military applications, and you might see Erica Violet used for OM4 in some cases, but that's usually limited to trunks and patch cords, very rarely to cables themselves. And on the right, you'll see the color codes for the individual strands within a cable jacket. So for example, if you had a 12-strand fiber cable, you would see each of those strands has that coloring scheme to readily identify during termination, so you can ensure proper polarity at both ends and readily fiber identification. If you have more than 12 strands, what you'll typically see is there'll be different binders supporting each of the 12 strand groupings. So you'll have a binder that might be a blue binder that wraps the first 12 strands, and then an orange binder that wraps the next 12 strands, etc. as you go through. Different manufacturers do it different ways, so it's just important to understand the methods used so you can properly identify the fiber for termination. Okay, so now that we've talked about the fiber cable itself, let's get a little bit into the actual connecting hardware that will be terminated onto the end of the fiber. The fiber connector types shown here are the most common fiber connector types you're going to see when you're working on optical fiber cabling. It's not to say that's all there is. There's a number of different legacy style connectors, anything from the FC or Frank Charlie connector to the MTRJ connector. There's Biconic connectors and SMA connectors. There's all sorts of different ones. But when you see, typical data commercial cabling, data center type of terminations, these are the four that are almost exclusively used, with ST being the oldest style for more of a legacy kind of 50 or 62.5. The SC is still fairly common for kind of standard density applications. And what you'll see is the LC connector on the top left is actually pretty preferred for most applications currently for single individual strands, simply because it's a small form factor fiber, meaning that it's got and terminates two fibers in about the same distance and the same size, I should say, as an ST or ST does in a single connector. So it's preferred to get additional density. And in the bottom left, we have the MPO or MTP style connectors, and those are fiber connectors that actually have multiple fibers terminated inside of a single connector. It ranges from it could be 8 fibers, could be 12 fibers, could be 24 fibers, and although Siemens doesn't currently offer them, they can actually be up to, I believe, 72 or 96 fibers now in a single connector. So depending on what your density requirements are, just always risky to have that many fiber terminations in a single connector. If there's ever damage to the end phase or something, you could be out of business for a lot of those, and that's typically not going to be a field terminated connector either, due to the complexity associated with that style of connector. So when it gets to actual polish types, or the actual end face of the connector themselves, what you'll see is there's really three out there. For all multi-mode applications, it's a physical contact style connector. So it's got a slightly domed ceramic ferrule on there with decent return loss in the area of about 30 dBs. When it gets to single mode, there's usually a much higher requirement for return loss. Standard single mode fibers have what is referred to as an ultra UPC, or ultra physical contact connector at the end. So it's got a little bit more of a radius dome and has a much better return loss of around 55 dBs or better. For some applications, however, even that is insufficient. They might be audio or video applications. It could be, just depending on the transmission, a lot of passive optical LAN systems use the APC style connector, which is an angled physical polish or physical contact style connector. And in that case, instead of having a radius end face, it actually has an angled end face and has exceptional return loss in excess of 70 dBs. The challenge there is it requires specific adapters and mates only to other APC connectors, because you effectively have to have the comparable connector on the opposite side of the adapter that has the 8-degree angle in the opposite direction for proper mating. So APC connectors are identified by a green color for both the adapters and the connectors, so that customers know what they're plugging into, and make sure they don't mix that between that and the standard UPC connectors, which are typically going to be blue connectors and adapters. So a quick word about kind of the reference language of, you'll see the words MPO or MTP. MPO is a multi-fiber push-on connector that we showed a couple slides earlier. MTP P stands for mechanical transfer plug, and it's really a superset of MPO. So MPO generically refers to that type of connector. However, MTP is a registered trademark of US Connect and really represents a higher quality connector than a standard MPO. So you can say that an MTP connector is an MPO connector, but not every MPO connector is certainly an MTP connector. So it has a number of advantages relating to the ferrule, the pin design, and the pin clamping that makes it a premium connector. And the MTP connector is used on all Siemens products. So we've talked about the connectors. Now, in terms of mating them and going from point A to point B, thinking almost like a copper patch panel, in a copper system, you typically have a female outlet and a male plug on there, and that's, so your patch panel is kind of a female outlet, and your patch cords are a male plug. In fiber, it's a little bit different in that it's more of a plug adapter plug design. So you have a plug on one side and you have a plug on the back side, and what we're showing here is the actual fibers adapters, and those are simply mechanical based adapters that really ensure proper alignment and mating of the connectors themselves. You might hear them referred to as certainly a coupler or a coupling or a bulkhead, but fiber adapters is the correct word for that. And while they're available individually for some instances, primarily what you're going to be specifying them for is adapter plates, as shown here, which go into enclosures which are typically 19-inch rack mounted. They may be wall mounted, and in some cases there's also fiber adapters available for faceplates. So for example, if you wanted to terminate a duplex LC connector at a work area, we have a duplex LC connector that snaps into the same opening as a MAX module would or a ZMAX outlet would. So in the next few slides here, we're going to talk about some of the different types of Siemens enclosures, just to give you an idea, depending on a project that you may have and which enclosure is the best. It's really kind of more of a selection process. So we'll start kind of more at the highest end, actually, which is the light stack enclosures. And these are referred to as an ultra high density type of solution, in that they terminate up to 144 fibers in a 1U rack mount space. It's ultra high density, but certainly very usable in this case. The limitation here is you really thinking about that kind of density, you're thinking about pre-terminated solutions. So it supports plug and play LC trunks, but it's primarily intended for use with the MPO based or MTP based solutions, where you're actually bringing a connector into the back of a module, shown on the left there, if you will, where the MPO plugs into the back of the module. Then there's internal harness wiring that brings it to LC connectors on the front. So no physical termination is required for that. So it's really referred to as type of a plug and play type of solution rather than fiber termination. So the density is exceptional. The operational and usage is actually exceptional as well. You just have to consider the application for actually deploying this. So it's got some nice features in terms of a sliding rear tray, in terms that it could be inserted or pulled out for additional access to connectivity at the back of the enclosure. And that front cover and the individual trays slide out with a front magnetic cover to kind of close it up and down. There's actually 3 individual trays in this enclosure, so you have accessibility to each of those as needed. The next enclosure, as we're kind of working down the density chart, is our high density fiber connect panel. And that's what we refer to as high density. So instead of 144 fibers per 1U, it's only 96 fibers per 1U. Now in this case, it's really targeted. You'll notice that the adapter plates here in the plug and play modules look different. It's because they are. The LightStack has their own designs, and the high density Fiber Connect panel system has its own designs as well. In the case of this one here, it's really, the whole system is based on LC and MPO systems, as is LightStack, so you won't see SCs or STs or anything like that with the higher density solutions. But in this case, you can do plug and play, you can do splicing, you can do field termination of fibers themselves. You have some greater flexibility here. In this case, the enclosure accepts up to 4 modules side by side in 1U, and the drawer slides out the front and out the back for accessibility. And we've listed here kind of the idea of how many fibers you can get in here for the different footprints depending on the module density, as well as the amount of splicing that can be performed in there. In this case, it's up to 72 fiber splices. So it's a 96 fiber enclosure, but based upon if you're planning on splicing, you have to realize that there's a limitation on the number of splice trays, which will limit you to 72. So the next one down, which is kind of referred to as a standard density type of fiber enclosure, because it really kind of bases on about 72 fibers per U space, is really our rack mount interconnect centers. And you can see here, this is the third type of kind of fiber adapters and fiber modules that Siemens offers. And these adapters and modules are common through this, as well as the next couple slides with the FCP drawer, as well as the wall mount interconnect center. So in this case, it's kind of most designed and tailored for a pretty good amount of flexibility, and that it accepts and works with. We have ST solutions, we have SC solutions, LC as well as MPO, and you can do plug and play, splicing, field termination. So this is a rack mount enclosure that ranges from 2U to 4U, where the adapters are horizontally mounted in the 24, 36, and 48 versions, and vertically mounted in the RIC 372, which accepts up to 12 quick pack adapter plates. So again, we've included the maximum fiber capacity as well as the maximum splicing capacity. And you can see in this cases, they're very well aligned in terms of overall capacity when working with like an LC fiber in terms of splicing. The next enclosure is effectively the 1U size enclosure of the RIC enclosures. It doesn't look the same as a RIC exactly, but it's really designed for that 72 fibers in 1U using those adapter plates. So same kind of connectivity is used for this as used in the RIC. However, this is specifically for the 1U application. So everything really stays the same. As I mentioned, this accepts up to 3 adapter plates, and there are 2 versions of this enclosure. There's a fixed version, which is the FCP3 rack, which is really designed to be very cost effective. It only hinges open on the back. So as long as you have clearance above it to work, it can be everything that you need for fiber. It doesn't offer any front fiber cable management or anything along those lines. So if you're looking for cost effective, it's a good fit. For the FCP3 drawer, that's a little bit more of a premium design, is that the drawer slides out the front and back like it does on the high density version of that, as well as the RIC enclosure, which slides out the front and back. And you also have patch cord management on that. So it comes down to some cases cost, and in some cases application need. And finally, we have the wall mount enclosures, which we refer to as our SQUIC enclosures, the Siemens Wall Mount Interconnect Center, and it uses the same adapter plates as the FCP3s that we just talked about, as well as the RIC enclosures. So the densities there, it's a little bit different kind of platform now, so you can't really compare them apples to apples, but it does have all the legacy type of fiber interfaces, including the ST and SC, but it does work with plug and play, splicing, and field termination. Just a reminder, in this case, there is a special splicing tray bracket that's required to mount the splice trays, and the splice trays are a little bit smaller because the enclosure is a little bit smaller, so the density capability for doing splicing is a little bit more challenging, as it's kind of shown there. So we have 3 versions. We have a mini splice tray, which accepts 2 of the quick pack adapter plates and does not provide a means for splicing, and then we have the standard and expanded versions of that, which accept up to 4 and 8 quick pack adapter plates respectively and support splicing with that splice tray bracket. So now that we've talked about basically the connectors and the cable, we're going to walk through some of the different ways that you can implement fiber effectively, how you can install fiber from point A to point B. So as you can see from this illustration, at the end of the day, we're really usually trying to get from one piece of equipment to another. And since it's optical fiber, it's typically not using the horizontal. So this is somewhere where 2 pieces of equipment are located within 2 different locations of the building. And as you can see on here, there's a number of different ways you can address that. There's everything ranging from splicing to trunking to actually directly connectorizing, which is just taking that raw fiber cable and putting connectors on it, as well as having pre-connectorized solutions, which is a version of trunking, but the plug-and-play solutions that we defined earlier. So let's go take a look at each one of those in a little bit more detail. So one of the factory termination solutions, and the one that's probably most widely deployed in data centers, is the plug-and-play systems. So in this case, you have MPO connectors on the end of a pre-terminated trunk that you're going to be plugging into plug-and-play modules on either side that are convert those to typically an LC type of interface that are just plugging the connections on both sides. So it's a nice design because it's really just a matter of installing it, plugging it in, and going to town. Like anything else, you have, in this case, you have 4 connection points on there that you have to manage, because cleanliness is a very important factor for optical fiber. But in terms of speed of deployment and support of higher speed applications, it also offers an upgrade path, because some of the higher speed 40 gig, 100 gig, 200 gig implementations are defined by an end-to-end MPO system and actually don't break out into LCs at the end. So it provides an upgrade path for those installations where a lot of the legacy solutions do not. Another solution is pre-terminated trunks. So in this case, instead of having an MPO connector at the end, you have multiple duplex connectors, whether it's SC or LC at the end, that can just plug into adapter plates on the back and then jumpers can be plugged into the front. In this case, the head of the connectors is going to be bigger than an MPO simply because, as almost shown here, you have 6 fibers or 6 connectors that total 12 fibers versus a single MPO connector. So it takes a little bit more care to ensure that those connectors are not damaged during that, but it does give you a nice, easy deployment method that doesn't require an MPO. So if you use an MPO system, you have some additional connectors you have to worry about. In this case, the connectors at the end plug right into an adapter, and then jumpers go into there, so the testing becomes a little bit easier. So these are available in strand counts up to 144 fibers, and they're available in multi-mode and single mode. So they do provide an alternate solution versus plug-and-play systems for a pre-terminated solution. Now, when it comes to field termination, you can actually do an epoxy polish termination where you're actually stripping kind of that coating off the fiber, and you're actually using an adhesive epoxy primer kind of combination that's inserted into the connector. The fiber is inserted into the connector, and then it's actually cut and then polished at the end. So it's a very high performance type of solution, but it's not for the faint of heart for fiber terminations. It's the most complex of fiber termination practices, and it's a very craft sensitive type of design. It just really depends on the preference and background of the contractors, but this is not really intended for rookie installers. It's certainly capable of being done by that, but you have a lot of parts and pieces that you're moving around. So if you were to do example terminating at desktops, you'd have to move all those fiber termination equipment from desk to desk to desk. If you're installing as a part of the backbone, which is more common, it's a little bit more manageable. It does have some consumables associated with that because the polishing paper and the primer adhesive would need to be replaced. Each of those kits last for about 200 connectors. But it is available for ST, SC, and LC connectors in both multi-mode and single mode, and terminates jacketed, which is typically like the 3mm jacketed fiber cable for like a maybe 1 or 2 fiber cable, as well as 900 micron tight buffered cable, but it does not terminate 250 micron cable. Now, a little bit more of an easier solution for terminating fiber, 900 micron type of fiber versus the polishing it itself, is to introduce a mechanical splice connector. In that case, the end face of the connector has already been polished, and there's a stub of fiber in there that goes back to what is referred to as index matching gel. So what you'll actually be doing is you'll actually simply be prepping the fiber, cleaving the fiber, and inserting that into the back of the connector, and then camming it to lock it into place. So it's a little bit less contractor dependent. It's actually pretty darn easy to do this reliably with fewer tools. The key here is a precision cleaver that's associated with that termination kit, which actually cuts the fiber and makes sure that that end face is in good shape and ready for insertion into the index matching gel into the connector itself. So a little bit more elegant, a little bit more, I would say, much more popular for termination versus epoxy polish in the field. But is limited to SC and LC only, multi-mode and single mode, and limited also to the 900 micron tight buffered fiber cable. So the third option for terminating field termination of optical fiber is our OptiFuse splice-on connectors. So instead, in this case, you're actually fusion splicing onto the back of the fiber stub that's in this individual connector. And it does require a fusion splicer, which can be a little bit of a pricey investment. They can range, I think, anywhere now between probably $5,000 to $6,000 up to $10,000 to $15,000, depending on the splicer that you use and the type of splicer system it is. But if you have invested in that, it's a very quick termination process, and without having to worry about splice trays, it's a little bit more elegant of a termination process than the pigtail splicing that we'll talk about next. It is available in SC and LC for both multi-mode and single mode, and the beauty of this versus the epoxy polish or the light bow mechanical splice is that it terminates both 250 micron loose tube as well as 900 micron tight buffered fiber. So the final option for field termination of optical fibers is simply splice on pigtails. In this case, there's a pigtail kind of shown on the left there. That's a kind of bulk pack of pigtails, and it has a 900 micron jacketing coming off the backside of it. And you introduce that into a splice tray where it'll be fused to the incoming fiber using a fusion splicer, which is kind of shown in the upper right. So it's a fairly elegant solution. It's not quite as efficient as a splice-on connector, but many people are a little bit more comfortable with that. Gives you a little bit of room for wiggle in case you need to do a re-splicing in case you have a high splice loss, for example. But It does require the use of splice trays in an enclosure, and as we talked about earlier, there are some limitations in terms of overall capacity with splice trays, which also take up a little bit more space in the rear of enclosures as well. So you have to make sure that that's something that's capable. But it is available for the full range of connectors, ST, SC, LC, as well as MPO and multi-mode and single mode, and works for terminating both 250 micron and 900 micron, which makes it ideal in some cases when you're transitioning within a building coming into 250 micron and you want to transition to a 900 micron indoor cable. Splicing is the way to go. In some cases, it's actually a splice on pigtails. In some cases, it's just splicing itself. So this table is kind of a high-level summary of the various field termination methods. And as you can see, a lot of it really just depends on the capabilities, the investment that you may have already made in, if you have a fusion splicer, it may be the capability of the technicians in terms of their experience in fiber. But Siemens certainly offers a solution that works for every application. So maybe it's a 250 micron versus a 900 micron discussion, or you need to terminate STs, which some solutions don't support. So, really break that down into what's most important for you as an installer. And then from there, it's pretty easy to repeat. Usually recommend investing in one or two strategies that you can use to address all the needs, and then continuing to deploy those regularly is usually the best type of practice. So we're going to spend a little bit of time on fiber polarity, simply because it's important to make sure it's done right. In a lot of cases with LC and ST and SC connectors, you can usually change that out at the jumper in the field if there is a problem. Many customers have their specifications already for the type of fiber polarity they want, but it really boils down to ensuring that it's done properly so that the systems operate as intended. So fiber polarity is a very critical element, not only during the planning phases, but primarily during the installation phases to ensure it's right. So you don't have to get into those situations where you have to worry about reversing some of the polarity on some of your fiber jumpers to make sure it's done properly. Fortunately, TIA 568.3 covers fiber polarity for both duplex and MPO style systems, and we'll cover those on the next few slides. So fiber polarity for duplex systems effectively boils down to this simple fact. The fiber, if you consider a two strands of fiber, a fiber pair, transmit and receive, the first fiber shall be at position A on one end of the link and position B at the other. The second one should be in position B at one end and position A at the other end. And so TIA recognizes two different ways that you can do that, which are consecutive fiber numbering and reverse fiber positioning, which we'll talk about. The important thing is they're both optically identical, and ensures that it both provide identical polarity and correct polarity. So these different polarity methods, these two different polarity methods are illustrated on this slide here. And in the middle, you'll see actually a fiber jumper in the middle. And you can see the purpose there is to illustrate that fiber position A on one side goes to position B on the other side, which is really just effectively the transmit going to the receive on each side. And what you'll realize is that these two methods are exactly identical. It just depends on how you want to deploy the orientation of the fiber adapter plates on each end. It determines kind of how you want to terminate your fibers, which order you terminate those in. So if you think about that, so consecutive fiber numbering, effectively you're going to install the adapter plates. And if you rotate those adapter plates toward the middle, so you're looking at the face of them, the adapter plates are oriented kind of 180 degrees on each end. And what that allows you to do is terminate the fibers in the same color, so starting top to bottom, if you will. So you could do blue, orange, green, brown as you go down and not have to reverse anything in that. But you do have to remember to have your adapters oriented opposite at both ends. For reverse fiber positioning, what you're going to be doing is the adapters are installed in the same orientation on both ends. Again, if you took those adapters and you rotated them towards, so they were facing us, you'd see the keys in that case would both be on the right side. And if you're doing it that way, then you're going to be doing reverse pair positioning, where you're actually alternating the fibers as you terminate them. So on one end, you'll be going, for example, blue, orange, green, brown. And on the other end of the fiber, you'll be going orange, blue, brown, green to ensure you have the proper polarity. Now for array or MPO-based polarity, there are a few options identified within TIA 568.3-D. There's actual three sample methods outlined, which kind of reflect options that are readily defined by the industry standards, and there are methods A, B, or C. We'll not get into the details of each one because they get a little bit more complex for an MPO systems in terms of keying of the adapter plates, as well as the polarity within the trunks or the breakout modules themselves. But it does cover the polarities A, B, and C for both duplex end-to-end systems as well as end-to-end MPO systems. So if you're going MPO all the way through and not breaking out into LCs, it's just an MPO jumper through an MPO adapter plate through an MPO trunk, etc. But we will summarize the pros and cons of each on the next slide. So the summary for an array or a plug-and-play type of system, an MPO type of system, it really kind of boils down to this. Method A doesn't really have any benefits for whether you're operating a duplex or a parallel, like a full end-to-end MPO system, simply because you need different jumpers at both ends for duplex, as well as different jumpers at both ends for parallel systems. For method B, it's manageable because you just have to have two different modules on each end, two different plug-and-play modules on each end. But it's if you do that, then you can use the same jumpers for both duplex as well as MPO systems in the future. So it's pretty simple to manage that. And it's something that's not really customer facing if those modules are installed, kind of day one. Method C is ideal for duplex systems. But when you get to the point where you want to transition and go MPO end to end, you do need unique jumpers at both ends for that. So not necessarily ideal for that. So if you really look at those at a high level, we don't really talk about deploying method A at all. Method B is what we typically specify if they're either already in a parallel or MPO end-to-end system, or if they're going duplex connectors today, like an LC, with plans to migrate to that in the immediate future. And if they have no plans to migrate and they just plan on going duplex end-to-end, we typically specify method C. So that should give you a high-level summary. As always, you can contact the Siemens TSG if you have any questions. A couple other considerations when using plug-and-play systems or MPO-based systems is simply that there is keying in the adapters themselves that you have to be aware of, key up to key down or key up to key up. So that has a lot to do and has to be considered if you're doing end-to-end systems, as well as pinning or gender of the connectors, because in order to ensure alignment of those multiple fibers, you will have a pinned connector on one side of the adapter and a non-pinned connector on the other side of the adapter. So it's important to understand both of those when you're designing a system. Typically, if you have a customer that's planning on migrating to a full end-to-end system, we would typically specify a male trunk and female cassettes, if you will, for the genders of the MPO, simply so when the cassettes go away at some point and you're doing an end-to-end system, you can use a female to female MPO jumper to connect to your equipment. And that makes it easy for migration, not have to worry about doing a male to female jumper and understanding which end has to plug in where. So it relates to that. Siemens does offer our trunks with MTP Pro connectors on that. That's something that's standard on our jumpers and kind of our hybrid cords, but it is an option for trunks. And having the MTP Pro connector on there does allow you to field change both the keying of that as well as the gender of those connectors with some relatively simple field tools. So it's something that makes sense to help people navigate this. It can be tricky at times, but if it's done properly, you shouldn't have to worry about that. But if something comes up in the field, it's always nice to have that flexibility. So that's it for Module 4 of Siemens Online Registered Installer Training. Next up, Module 5, Fiber Testing and Termination.